Hi there, welcome to this new project, and in this project we will look at a different technique today where we will going to do the prediction of housing data or housing prices based on some variables. So this is different than what I have shown earlier, and this is again a new Python project that I'm showing you. And as you can see, the data set that we will going to use is the Boston housing prediction data set. And with the help of the variables and the techniques we will be applying in this particular project tutorial, you will see that how you can take these techniques and apply anywhere else. Let's say if you want to experiment on your own with the data that you have in your hand. So let's go ahead and see how you can do that. Well, first of all, importing the relevant libraries. So import pandas as PD, import matplotlib dot pyplot as plt, import we will going to use the seaborn library as well in this case, because we will going to plot some regression plots. So seaborn as SNS and percentage matplotlib inline. Also, as and when the requirement will arise, we will go ahead and see the relevant library and import it. Okay, next thing is the loading the data set. So what I have is basically the CSV data set. So what I can do is simply say Boston equals to pd.read underscore CSV, and it is boston.csv surrounded by the quotes. If I execute it, it will execute fine. And if I just want to see the data, that's where my data set is. That it basically shows the different columns like CRIM, ZN, and so on and so forth. They basically have their relevant meaning, and if I just show you their relevant meaning, it's basically over here, CRIM, and if I just change this to something which is RB, raw NB convert, so this will be with you. So CRIM is basically indicates the per capita crime rate by town, and so that means higher the crime rate, there will be a less occupancy or there will be a less price. And this particular column MEDV is basically the median value of owner occupied home in thousands of dollars. So it's nothing but the price, right? So you can even change this column name to price, but I'll just keep it as it is since we have the representation over here. Description. But if you see other like LS stat, which is 1% lower status of population, so higher the percentage of lower status population, that means lesser the value. And same is the case with if you see ZN, proportion of residential loans zoned for lots over 25,000 square feet. Similarly, INDUS, which is the proportion of non-retail business acres per town. So all of those different things which impacts the housing prices, they have gone ahead and collected it. All right, so now let's move ahead. So the first thing we will going to look at over here is basically the description of this and all these columns. So for that, what I'll write is Boston.describe method. And if you have seen my previous video, that's a very common method that we use, and it basically shows the count of rows, so it can indicate whether there is any missing values. So yes, if you see, the 506 is basically the overall count, as I can see it from the other columns, but in many columns the count that is present is 486. So that means there is some missing values. And then you have the respective mean, standard deviation, minimum, 25%, 50%, 75%, and so on and so forth. So all of these values which are relevant for, or which are coming out from this particular data set. So what do we do with the missing values and all? We will going to look at that. So one of the easiest method is simply Boston.dropNA, which will going to drop the NA, that means the missing values where they are present. So if you see that it has given you this data set, and the resultant is basically the 394 rows and 14 columns. So what I need to do is I need to just say in place equals to true, and if I go ahead boston.describe method again, we have actually lost a lot of different rows. If you see over here, so we had like rows over here 486, 486, so 506. So it's up to us what method we want to choose, whether we want to apply some other technique, like for example usually it has been applied that whatever the previous value is, just go ahead and replace it with the previous value, because it is like, if you have seen my regression, the linear regression or the time series models that I have posted earlier, the projects, it basically reflects that the naive model or the basic model is that previous value is the best reflector of the current value. So that's why that's the assumption that goes when you replace the null values with the previous values, or sometimes they can even go ahead and create even the regression model separately for filling up the NA values. Right now we have chosen this method drop NA. We could have simply saved 0 also, in case if you wanted to fill the missing values with 0, right? Or it can be average as well, the average of values. So all of those are different methods that one can apply, but for now we will just go ahead and fill this up. However, it is in best interest that you basically spend a couple of hours just to evaluate that whether the drop NA or replacing the missing value with 0 values, or with the average values, or with the median values, or a separate if you need to build a simple regression model only for replacing the values, you should always check with that. But for now I'll just show you some of the correlation or the regression plots with the help of the SNS method or the SNS library, which is seaborn library. Helps us see how the a scatter plot along with the regression line on it. So sns.regplot is basically the method, and where we have to specify the x and y values. So we'll specify x as RM, which is nothing but the average number of rooms per dwelling. So if the average number of rooms are increasing, what we can assume is the price will also increase. So this way you will have some positive upward correlation. So data equals to Boston fit underscore reg equals to, we'll just say, okay, yeah, go ahead and make it true, and we will give it a title. So plt dot title relationship between rooms and price, simple, right? And simply say plt dot show. All right, so it has given the error with the price. We have MEDV. Yeah, if I go back, yep. So that's our plot, and as I had assumed just a few minutes before that, it will be a positive correlation over there, and that's what we have seen. Now let's see with the lower status population, which is nothing but this LSTAT, percentage lower status, and my assumption is that it will be a negative. So this is a positive correlation, but with the LSTAT column it will be a negative. That means higher the population, lesser the price. All right, so let's test that. SNS dot right plot and y equals to MEDV. We can have x or y as an so like in this case we had x first and y later. I can even have the y first, so there is no issue on the ordering of the parameters. So it's just that where we want to put the parameters or the columns over here. So data equals to Boston and fit underscore rank equals to true, and we'll simply say plt dot show. You can give any title, like for example relationship between the lower status of population and price. So this, as I assumed, higher the LStat, the column, lower the value, right? So this is like pretty basic, because number of rooms in this case, if you see that it has the number of rooms are increasing, the price will obviously increase. If you have the more lower status of population, the prices will decrease. That's like a society trend. Now let's see an interesting observation, which is nitric oxide concentration, parts per 10 million, which is basically related to sort of a pollution related stuff. And I expect that higher the NOx parameter, this particular NOx parameter, or the NOx column value, that means lower should be the prices. All right. So SNS dot reg plot, and we can have x as NOx, right, and y as MEDV. All right, data equals to Boston, the same parameters, and I believe that once you will practice this couple of times, you will be you will have no issues in doing it. So there is a negative correlation. If you see the NOx value, as it is increasing, the prices are decreasing. All right, now let's try to evaluate the the relationship between the prices and the weighted distance between the 5 Boston employment center, which is nothing but I believe is the DIS, yeah, weighted distance to 5 Boston employment centers. All right, so what do we need is simple, again, reg plot, and within that we will see the MEDV and x as DIS, and then data equals to Boston, and fit underscore reg equals to true plt dot show. All right, so as expected, if the number of if the distance is bit high, right, there is a positive correlation in that. So all of these are basically showing you what sort of relationship that each of these variables are having. Now let's try with another variable, which is PT ratio, people teacher ratio in town, for those who are having children, right? So SNS dot reg plot, then x equals to PT ratio, and y equals to MEDV, okay, comma, data equals to Boston, and fit underscore reg equals to true plt dot show. And as the PT ratio, the people teacher ratio, is increasing, lower the prices as expected, right? After that, let's try with the crime rate. That means higher the crime rate, lower should be the prices. That should be our hypothesis or assumption. So SNS dot reg plot, we will say x equals to CRIM and y equals to MEDV, data equals to Boston, fit underscore reg equals to true plt dot show. All right, okay, what I'm doing with this, plt dot show. Okay, so negative correlation, as you would expect, along with some critical boundaries that it is giving you the information. So that's about how these relationship that exists, some of the important variables. However, it is always beneficial that we are checking with all the different variables. For example, proportion of non-retail business acres, or Charles River dummy variable, that is 1 and 0, so it will not give us the output as we are expecting, but proportion of owner occupied built prior to 1940, right? All of these will basically give you the information about how the relationship is, or index of accessibility to radial highways. So very, very important variables, but where we have looked at couple over here. Now let's see some histogram, and one histogram that we can see is basically related to the crime rate. So plt.hist is the method that we can utilize, and we can write like boston.cr, boston.crim. If you see, it shows that this is very, very left or the right skewed like this, and does not show a normality. So what we usually do is sometimes we normalized our data points just to see whether is there any normality which is inside it. And one of the ways is basically to do a log transformation, which basically sometimes reflects its true picture. So over here what we can do is we can simply say np.log and then log. I believe I have defined np, if I am not wrong. No, I have not. Okay, all right. So I'll press A and simply say import numpy as np. Right, so here it shows sort of a normal distribution once we have taken a log of it. So log does nothing, but it basically normalizes your data points whenever it has some some exponential decay or values which are like extremely above, and just try to normalize that so that you can see whether it really follows the normal distribution or not, right? So in this case it clearly reflects that it is following a normal distribution. Now what we can do is we can have another histogram, which is nothing but the number of rooms, right? So it also shows that it follows sort of a normal distribution, and then we can have another one which we evaluated earlier, which was nothing but lstat. So it is slightly right skewed. So in these cases we don't have to do a lot of the log transformation and all. It's just that in case of the crime data, it was like heavily the data was not that much or properly distributed, so that's why we had to take the normalization, the log for normalizing the data for histogram. Similarly, what we can do is we evaluated another variable, which was NOx, the nitrogen oxide. So boston.nox, if I put it again, it is very right skewed over there. The next one is basically the plt.hist and Boston dis, right? So it's all sort of very right skewed, as you can see from this structure. So the last one can be the pupil teacher ratio. So boston.pl, or we already did that. NOx, lstat we already did, and we'll just check the PT ratio. All right, let's come down. Dot PT ratio, and that is heavily left skewed, as you can see. Okay, so let's move on and also just try to understand the correlation between the values that we have. So for that, we can simply pick up the columns of our interest. So we have Boston.columns. So we have this index. starting with 0, 1, 2, 3, 4, 5, 6, and the column that we had seen is basically the CRIM, and then we have seen the NOx, so 0, 1, 2, 3, 4. We have seen 5, fifth column, then we have seen DIS column, and then PT ratio, and so on and so forth. So what I'll do is I will create the Boston underscore selected underscore var underscore df, right? And I will say that Boston dot ILOC, which is by using the integers we will be selecting the number of columns. So here colon indicates that all the rows, and the columns we can specify over here. So 0 because we need crime rate, 0, 1, 2, 3, 4, which is NOx, what we evaluated earlier, 5 because RM5, 6, 7, 7, 8, 9, and then 10 PT ratio. So 10, 10, 11, and 12, right? And then we have this particular crime rate as well. So let's go ahead and take that as well. So we have already taken that 0, right? So let's go ahead and see. So Boston underscore df dot head, and here is our this all data frame with all the variables that we want. What we have not picked is basically the price, because, or MEDV, which is our target variable. That's what we want to predict. So we just want to understand the correlation between the independent variable. So before we do that, we will just do take a log of crime just to make it normalized. Selected, and then CRIM, and then np.log, and Boston dot CRIM. All right, so we'll go ahead and execute it, and I will just evaluate this by using the head, and yeah, these are all transferred into the log. So I'll just go ahead and ignore the warning, which is a setting with copy warning. A value is trying to be set a copy. It's a slice from a data frame, so I'll just ignore that for now. Okay, so now our data set is ready. I can go ahead and use or figure it out the correlation using the core method. And this is our correlation. So with same variable it will be a perfect correlation, but if you see CRIM and NOx, it has some positive correlation. With room it has negative correlation. With DIS it's some positive correlation that is present. So over here DIS and NOx has some positive correlation. Similarly LSTAT and so lower status and the crime rate has some positive correlation. Yeah, this particular the room and lower state population, yeah, it has some negative correlation over here. So this basically indicates that these are the values which basically shows that there are some correlation that is present among these values and can be used in the predictors, or can be used as predictor. All right, so now let's go ahead and create a model out of it using the stats model, which has the simple ordinary least square method. So statmodel.api as sm, and then from statsmodel dot formula dot api import OLS. So once it is imported, we can go ahead and define the model. But before we define the model, we need to make sure that the variable, which is price, is part of this particular data set. So what I'll do is I will say Boston and make it a price, and that is basically part or boston.medv, right? So if I just go ahead and execute this and just say that Boston underscore selected df head, now I have the price as well. So I can have the model, and the model will be based on the ordinary least square, the small OLS, that's what it indicates, ordinary least square method. So which is basically for estimation of unknown parameters in linear regression model. And here we will indicate price tilde. This is the part of the formula notation that we need to specify when we are using this. So we have the crime rate plus NOx plus RM plus DIS plus PT ratio RATIO, right, plus LSTAT, all right, and then the data frame is this dot fit. Let's go ahead and execute it. So our model is created and it has not given us any error. The simpler to again rephrase this, we want to predict the price, that's why we have used this first using the variable this, and that's basically a notation that hey, predict this variable using this variable of this data set and fit the ordinary least square model, which is a linear regression. So what we can do is now we can print the model dot summary, and once we print this, it's a pretty well formatted summary. And over here, if you see, there are variables, for example, so we have an intercept, we have NOx and crime rate, DIS, PT ratio, LSTAT. Very first thing which I will see is basically the statistic p-value, and wherever the p-value is lesser than 0.05 I will reject that. But if you see in the case of the crime rate, it's 0.640, that means it is greater than 0.05, which is a threshold value for p, and this will basically indicate, or this is indicating, that we need to remove the crime rate as it is not a very significant variable. So the significance of a variable can be identified using the p-value, which is having a threshold of 0.05, saying that if it is, the value is lesser than 0.05, then accept that, and if the value is higher than 0.05, in this case 0.640, then do not use this as part of the model. Along with that, you have different statistics like omnibus, probability omnibus, skewness, kurtosis, Durbin-Watson, Jark-Bera, all of those which right now I am not explaining, but something to take care of. For example, in case of Durbin-Watson, I remember it's used for the checking the autocorrelation, and if the value is above 2, that means the autocorrelation present. So we will, once we check the assumption of autocorrelation that these variables are not significantly autocorrelated, then you will going to go ahead and check the Durbin-Watson statistics. So there are different statistics which it's print. Similarly, AIC and BIC, in case of the time series, I informed you about or explained you the archaic information criteria or Bayesian information criteria, what they indicate and how we need to use this. So let's go ahead. So this is what we get, and intercept is basically indicating a value of 36 over here, whereas so these are the coefficient value, and the coefficient crime is, as you can see, is 0.06, NOx is -21, indicating that if we increase or if we take this value into the consideration, the value will have a negative impact. That means it will reduce the value of the price. As you could see above there also, that it has a negative correlation. So if I just show you NOx, it's a negative correlation, and that's why down there we get the output also as negative 21. Also from the interpretation perspective of in the real value, which is nothing but the price, what it indicates that as the average room will be increasing, the price will be increasing by the $4,488. So that's what it basically indicates. Similarly, NOx, based on the unit which is given in the data set, per unit increase will basically going to decrease the prices by the $21,000. So that's what it basically interprets when you try to interpret the variable. And one other important metric that we have is basically the R squared, which shows that all the variables that we have chosen, how much they contribute. So right now it is 73, and adjusted R square is basically indicates that as we increase the value, or as we increase the number of parameters, for example CRIM, NOx, and all of these, suppose tomorrow we want to add new one, whether the value is increasing or decreasing. If it increases, that means it is good. So R squared will going to always increase whenever you will add a new variable, but adjusted R square is the real metric to understand, because it really checks whether the newly added variable is contributing significantly or not. If it is not contributing, the value of R squared will be decreasing. And as you can see over here, the normal R squared value is 73. That means these variables contribute 73% into the model. But adjusted R square is saying that no, it is 72%. So there is one variable, or we can basically do a check on the variable by removing or adding it, that how much they contribute, and that's like a separate altogether, which is like called called parameter tuning. We keep on adding or removing the parameters based on the column that are present and checking what is the adjusted R square value. So all of these is something you need to take into the consideration when you are producing the model. So after that, let's try to forecast or predict the prices, or I'll say predicted prices equals to model dot fitted values is what the property that it has. So if we execute this, and if I just say predicted prices, these are all the predicted prices that we have. And now what we can do is we can display both the predicted prices and the actual prices. So plt dot scatter, and we have Boston dot price comma predicted prices, and it shows a good positive correlation. That means so what it basically indicates that since it is a good around 45-degree good momentum between the actual and the predicted prices, this model is something that you can use for doing the prediction of prices, because they are moving along the line. If they will be moving up here and there, that would have been some problem. But even in this case, there are some outliers like this, which are basically skewing the results a lot, or this will be deviating from the pattern and give you a little bit weird results when you will try to predict it. Another thing that we can basically check is basically the error rate. So from sklearn dot matrix we can import the mean squared error, and we can say that error equals to np.sqrt, just to get the errors into the right term, because this will going to square the error and this will remove the impact of square, so that we can get the error terms in the same way the prices metric is, or the price unit is. So np.sqrt mean squared errors, and we have the test values, which is nothing but the prices. So Boston dot price, and then predicted prices. And if we see the error, so right now the error is around 4.7, so it's like $4,732 is basically an error rate, which can be plus minus $4,732 can be the variation which can come when you are taking the help of this model and try to predict it. Now what we can do is we can employ other methods. For example, so right now we have taken this on the entire data set. We can always do a train test split, and we can check whether this is further improving or decreasing, because right now we are training on the entire data, and we are testing also on the entire data. That means this is a good view of, or the case of a model where the model has not seen the unseen data. So what you can do is basically another quick thing which I would just show you over here is how you can basically get the split the data into train test split method. So what I'll do is from sklearn dot model selection import train test split. All right, and what we'll do is we need to identify the dependent and independent variable. So for that we will say x equals to Boston, right? And in the x, that means the independent variables, we need all the variables but not the price variable. So we'll just drop the price variable, price, and we indicate that we want to drop it from column. So access equals to 1, and y equals to Boston underscore selected, and we want only the price. All right, and then we will say x underscore train, x underscore test, y underscore train, and y underscore test. So this is basically a methodology for train test split, and we will say train underscore test underscore split x comma y comma test underscore size. How much, what will be their test size? So generally it is 30%, so I will indicate 0.3, and so that you have the same result as mine, I will say random state equals to 3. It can be any value. It's just to make sure that if you specify random state 3, whatever result I'm producing it over here, you will be getting the same result. Sorry, small x, small y. So now we are good. So now let's go ahead and try to fit the model and try to see how well our model is doing on the test on this particular data. So we have used the OLS over here, as you could see, but as we are moving it over here with the train test methodology, what I'll do is I need to import the sklearn dot linear model and import linear regression. So just trying with another, not just with the OLS method, but with the linear regression. So sklearn also has this. It's just that it does not print the summary statistic like this, which I really like. So you can use any of this method which you like, but just wanted to show you a different method here. So first of all, we will initiate the model using linreg, linear regression. You can have Boston linreg or any other that is in your mind. So we initiated this, and then we will fit it, linreg dot fit x underscore train comma y underscore train. So we are taking both x and train, y and train, not the test, because test is our holdout data set. And now when we want to predict it, we will use y underscore pred li linreg dot predict, and using the holdout. So x test is something which is 30% of your values, as we have indicated it over here, that test size is 0.3. So now y prediction has come, and what we can do is we can, like earlier, we can plot the value plt dot scatter and y underscore test comma y underscore pred. And this also shows, if you see, a good positive correlation or the good positive outcome, which indicates that yes, our model is working fine even on the unseen data, and we can even have the error rate. So np.sqrt mean squared error, and we have the y underscore test comma y underscore pred prediction, and we get like 4.39, which is very similar to what we got over here. So in this case, our error rate is further improved a little bit. So now with this, as you can see, you can employ these different techniques, like the linear regression that we have chosen specifically because we splitted the data set into train test, and we wanted to see how the model is performing on unseen data. But what I would really like is right now I have just chosen the specific columns for the purpose of this demonstration. What you can do is you can have the model on the entire column, right? Or just experiment with the couple of different columns like age, like tax, or ZN, and all of these columns, and see how you are getting the results. So with this, you will have a good practice, and you will be able to see that adding or removing the variables, how it impacts the values like R square or adjusted R squares, and over here whether they are satisfying the criteria of our P statistics or not. So that's pretty much I wanted to discuss in this video. However, there are various things which are still there. For example, checking the residuals, checking the QQ plot, which is basically for checking the model assumption whether the errors are normally distributed or not. But I'll cover it in some other video. I know we have covered a lot in this video, so I hope you will build your basics with this. But yeah, let's discuss how we can evaluate the models in a separate video altogether. So let me know, what do you think about it? What do you want to learn more from my videos, where you want me to focus more? I really appreciate your comments, and don't forget to share it with your friends and colleagues. Thank you.